Let's take a look at lesson 16.1, segment length and midpoints. This is the first lesson in this unit where we're going to start dealing with geometry. And in geometry, there's a lot of vocab words, a ton. So you're going to see a lot in here. And we start with what we call undefined terms. Undefined terms, they're called undefined because we have to use these three figures in order to define everything else that we use in geometry. All of our other definitions are going to be using either points, lines, or planes. And when we come up with more definitions, we kind of add that to our toolkit. We'll also come up with statements that uses our undefined terms and our defined terms. So let's start with point. A point is a very specific location. It has no dimension. So if you hear me refer to it as 0 dimensions, right? It doesn't go up, down, left, or right. It's just one very specific location. This is what it looks like. This is how we label it. We'll have some practice with this later on. A line is made up of a bunch of points. And it says it has no thickness, continues forever in both directions. This has one dimension. So remember, the point is 0 dimensions. This is 1 dimension. So it's a length. This is what it looks like. You see the capital letters are identifying the points, 2 points on the line. This cursive lowercase letter is just another way to label the line. And these are the ways. You can see there's 1, 2, 3, 4, 5 ways to name a line. And the last one is a plane. It's a flat surface. So this lives in the 2-dimensional world. So you can picture something like a floor on the ground that goes forever in all directions. That will make up a plane. This is what it looks like. You can see it contains 3 points. Think about why we'd have to put 3 points in here as opposed to 2 points for a line. This script letter, again, uppercase, is another way to label the plane. And so here are ways to name it. We have some more terms right below. These are called defined because now we get to use points, lines, and planes to make up these figures. So the first one is a line segment, and it's part of a line. Remember that a line goes forever in both directions. A line segment doesn't. It has 2 endpoints. That's what it looks like. This is how we label it. A ray is also a part of a line. It has 1 endpoint, and that's it. And it goes forever going the other way. Okay, and that's what it looks like. That's how we name it. On page 776, we're going to practice drawing some of this. I'm going to do one of them. I think I'll do D, and I'll have you practice the rest of those. So on part D, we're just going to sketch it, exactly what it's telling us. We're going to draw 3 points, J, K, and M, so that they are not all on the same line. If I actually ask you just to do this on your own, yours is probably going to look different than mine. But you just draw your point J, point K, and your third point just needs to be anywhere except for this imaginary line that's going through JK. It can't be on that imaginary line. So I'm just going to put it down here somewhere. There's my point M. And then we want this to be on a plane that contains those 3 points. And it says you might also put a script letter such as B on your plane. Remember, that's another way to name it or to label it. So my plane, I'm going to draw it like this. And you're imagining this plane to kind of be flat on, let's say, your desk or your table. So it is parallel to the ground. And I'm going to put this script letter B down here. You're usually going to see a script letter in one of the corners of your plane that you draw. Doesn't really matter which corner. Just kind of put it out of the way of the other point so you don't get it confused. Now I want you to try parts A, B, and C before you see my solution. And then after that, we're going to learn how to label these just right below in part E. In part A, we draw 2 points, J and K. And then we're going to draw a line that goes through them. And remember that every time that is referring to a line, it's always going to have those arrows. It goes forever. If it wants endpoints, it's not going to call it just a line. It'll call it either a line segment or array. In part B, we have J and K again. And we're going to do a line segment this time. So here's my line segment. Yours doesn't need to look exactly like mine, but it should have the 2 endpoints where one of the endpoints is J, the other one is K. And in part C, we're going to draw point K, and that's going to be our endpoint, and we'll draw our array going any way that we want. And along that way is point J. So it should look something like that. In part E, we're going to go ahead and label or come up with the names for everything that we drew up at the top. So our points, we would have to say the word point. So we would say point J, K, M. If we're referring to each of those separately, we would say point J, point K, point M. But it's okay to just list them if you're only talking about points and there's multiple points. For a line, we have multiple ways. We can write JK with, I'm going to call that a line notation or a line symbol right above that has the 2 arrows to show that it's a line. We could also write it like this. I prefer the first one. If you want to think about why. You could also say line, the word line, JK, like that. And I can't really fit it, but you could also write down the word line, KJ. So we have 4 different ways in just how we drew it. For a segment, that's part B. It looks like I can label this as JK with the line segment symbol or notation above it. Notice I have no arrows there. We could call it KJ. Or segment, we could write the word segment. And I could use JK or KJ there again. For array, this one's a little bit more restricted. I have to write it like this. Or this is the way you're normally going to see it written. Let me zoom in a little bit. So I wrote it as KJ. And I put a array symbol above it where the arrow is pointing towards J. If you write it the other way, like JK, like this, you could do that, but make sure you have it pointing the other way. You won't normally see books write it that way. You won't see that in any selected answers, but that is an option for you. The default is just going to be this first one. It's going to start with the endpoint and then go to the other point. And obviously you could also write Ray, K, J. And this one has to start with K. It has to, because you have to start with your endpoint. And the last one, plane. We could say plane J, K, M, or plane B, the script letter B. On page 777, there's some more vocab for us. And you've heard of the word parallel before. So I'm not going to talk about that one. But we have coplanar, collinear. You can think of like the word coexist, like at the same time. So coplanar would be points that are on the same plane. Collinear would be points that are on the same line. So coplanar, collinear. They also have the words non-coplanar, which is just the opposite of being coplanar. And they have I think it's non-collinear, something like that. So just understand what just the root of that is. A postulate, I don't know why I don't have theorems in here, but a postulate is just a statement, a math statement, where we're using our previous definitions or previous statements we've made that are true. So a postulate is just going to be a statement that we accept as true. We also have things called theorems, like if you've heard of the Pythagorean theorem, is also a statement, just like a postulate. But theorems, we can actually prove why they're true. Postulates, you're just going to trust me that they're true. Or when I learned it, that was the same thing, right? There's just a statement that's true without any proof. The first postulate you see here is called segment addition postulate. All this says is when you add two parts of a segment, let me highlight this for you. Two parts. So if you have that segment AB, and if you have this segment BC, and if you add those two together, you get the whole thing. It equals the whole thing. That's all that. I drew it too long, but that's what this postulate is saying. Add up the parts to make the whole, that sort of thing. So on page 779, we're going to take a look at the distance formula. The distance formula comes from the Pythagorean theorem. So if you know how the Pythagorean theorem works, we're pretty much doing the same thing here with the distance formula. The good news for you guys is I'm not going to make you memorize this. You just have to know how to use it. And once we start using this some more in class, I won't do this formula step by step. In fact, I actually think about this formula a different way. Sometimes I don't even memorize the formula myself because I don't use it directly. But I want you to pay attention to the graph here. It's showing a shape that looks like a right triangle. And this is the actual formula. If you want to highlight this or box it, here's the formula. All right, it uses x1, y1, x2, y2. It squares some things, just like in the Pythagorean theorem. It adds them together. And then it takes the square root because that's how we solve Pythagorean theorem problems, is we take the square root to get to our answer. So let me show you how this works on the graph and why it relates to Pythagorean theorem. This side on the very bottom of your right triangle is actually this. If you subtract your x coordinates, it's telling you how long it is going from side to side. So the x coordinate, x2 over here and x1 right here, you're subtracting it to see how long that is. For the y, this part right here is the y2 minus y1. So you're trying to find out how tall this triangle is going from y1 to y2. So you're subtracting those. That ends up being your two short sides of your right triangle, your A and your B. You're squaring them, you're adding them together, and finally taking the square root. So that's all that's going into this. So if you feel comfortable understanding it that way, and you want to do distance using right triangles and Pythagorean theorem, you can do that instead of using the formula. On page 780, we have just one your turn, but I'll let you do half of it. We're going to determine whether segment JK and segment LM have the same length. Justify your answer, meaning they just want us to show our thinking, show our reasoning as to why they have the same length or don't have the same length. Anytime it talks about length, that's the same thing as distance from one point to the other. So if I want to find the length of JK, and I'm only writing JK with nothing above it, because once I do that, I'm talking about the length of it, or the distance from J to K. That's going to equal, and then I'm actually going to use the formula just for the sake of you seeing how this works. And I did forget something. In order to use the formula, you need to know what the coordinates are. So the coordinates for J looks like -4, 4. And K is -2, 1. In our distance formula, we're just going to subtract the x's Our x coordinates are -4 and -2. So I'm going to do -4 minus -2. I'm going to subtract the y's. That's 4 minus 1. Make sure you put a squared above each of those things that you're subtracting. -4 minus -2, that gives us -2. 4 minus 1 gives us 3. Square those. I get 4 plus 9. Once you get to this part of the formula or this process, you will have all positive numbers, right? When you square negative numbers or you square positive numbers, it's going to turn out positive. And if I add those together, I get the square root of 13. I am fine if you leave it like this. We can't take the square root of 13 very easily, right? Square root of 16 is the closest. We know that that's going to equal 4. If you want to put this in your calculator and get an answer, you don't actually have to do this, but you could put in your calculator and it'll be 3 point something. But you can also leave it as just the square root of 13. Okay, go ahead and try to get the length of LM before I show that on here. To find the length of segment LM, using the distance formula, I'm going to subtract the x's, and that's -1 minus 2. Make sure you square it. Subtract the y's, -4 minus -2. Square that. That gives me -3 for the first part and -2 for the second part. Square each of those. Remember that those will give you positive numbers since we're squaring it. That's 9 plus 4, which is the square root of 13. So this is our justification to show that the lengths are both the same. So then we can conclude that again, that they are the same. The last thing we're going to look at is midpoint of a segment. So just below our example here, the midpoint is the point, it's the location that's going to cut our line segment in half. So it splits it up into 2 equal parts. If you draw a line, array, or anything that goes through the midpoint, we call that figure a segment bisector. So looking at this figure right here, or this diagram, M is the midpoint. This is just notation to say that anything that has that hash mark is the same length as any other thing that has the same mark. Okay, this is a line. You can't cut a line in half because it goes on forever. But this line is a segment bisector of this segment right here. It cuts it in half. On the next page, I'm not going to go through this, but you can follow these steps if you want to physically find the midpoint of a segment. So you do it by folding paper. On page 782, this is what we're interested in right now, at least. The midpoint formula. So in the midpoint formula, we're doing this. You see it has x1, y1, x2, y2, just like distance formula. All right, in order to calculate this, we're looking at 2 points. And then it shows you a picture of what that looks like. So if you have point A and you have point B, you can use this formula to find that halfway point, right, that midpoint. Okay, so we're going to practice this just right below. One thing I need to mention is that midpoint is a point. That means you need to have an x and you need to have a y. So the midpoint should be written in the form of a point. I'm going to do number 12, and I'll have you try number 11 after that before I show the answer. So number 12. Directions, by the way, say show that each statement is true. If segment JK has endpoints of 7, 0, and -5, -4, then the midpoint M of JK, segment JK lies in quadrant 4. Quadrant 4, a little bit of review. Here's our x-axis and y-axis. Quadrant 1 is up here. Quadrant 2, top left. quadrant 3, bottom left, quadrant 4, bottom right. We want to show that the midpoint of this segment JK lies in that bottom right part of the graph. And all it takes really is just to find the midpoint, right? Everything in the bottom right of our graph means that x is going to be positive and y is going to be negative. That's how we get there. So let's just calculate the midpoint. Midpoint M, let's use our formula. Here's an easy way to understand the formula. Just add your x's together. Or really what you're doing is you're finding the average of your x's and you're finding the average of your y's. So you add them together, divide by 2. I have 7 plus negative 5. Those are my x coordinates. Divide it by 2. Add the y coordinates, 0 plus negative 4. Divide it by 2. And remember, this is written like a point. It's in the parentheses. It has a comma in between the two parts of the formula. If I add 7 and negative 5, that's equal to 2. Then divide it by 2, I get 1. 0 plus negative 4 is negative 4 divided by 2 gives me negative 2. So the point M, 1 comma negative 2 does lie in quadrant 4. So you can stop there. You can state that it does lie in quadrant 4, but I would accept you just leaving this as it is. Go ahead and try number 11. For number 11, you see the numbers I plugged into the formula there. We want to prove that the midpoint is the origin, so you need to know what the origin means. And if we actually just worked out the formula, then we would get 0 divided by 2 and 0 divided by 2, which ends up being 0, 0. And that is the definition of the origin, or that's what that point is. So this is enough to show that the statement is true.